Alrighty, so this video we're going to start our foray into the use of Schrodinger's equation. Basically, we will go step by step through a number of systems that are able to be solved either by hand or by computer or numerical methods. And what you're going to find is that there's really not that many. There's only a few problems that we can do, or at least we can do exactly. There's, of course, an infinite number of problems that can be done, but the solutions to which must be done by approximations or fancy techniques that don't give the exact answer, but give a good approximation of the answer. And so the first system is what's called the free particle. This is a particle, so let's say an electron or a proton or a neutron or something, a particle that just travels through a vacuum. There's no electric field, there's no gravitational field, there's no other particles involved. It's just a single particle moving through a vacuum, untouched or unmolested by outside influences. And what we would like to do is define the wave function for this system. And the reason, of course, is if we know what the wave function is, psi, then built into this function, this wave function, is everything we could possibly know about the system. So, for instance, if we know psi, if we know the wave function, then we can ask questions. We could say, okay, given this is the wave function, where am I most likely to find this particle? Or what's the most likely momentum for this particle to have? And if not that, what about the second most likely or the third? What are the probabilities of the different momenta a free particle can have? Or what are the different energy levels? How much energy can a free particle have? And things like this. In order to ask such questions, and when I say ask, what I mean is in order to theoretically calculate the answers, we need the wave function psi that describes the system. How does one get the wave function for a system? The use of Schrodinger's equation. So if you remember Schrodinger's equation, it says minus h bar squared over 2m. Second derivative of psi with respect to x squared. We're doing this in one dimension, so just one, just the x direction or just the y direction, whatever. Plus whatever potential is acting on our particle times psi is equal to E times psi. This is Schrodinger's equation. It's a differential equation. It's got derivatives in it. Second order, because the highest derivative in this equation is the second derivative. So it's a second order differential equation. Partial differential equation, because the derivatives are not total derivatives. These are partial derivatives. And so in order to solve for psi, we have to solve a second order differential equation. So how do we set up a system in general? In general, this is always going to be your equation. You'll always write this down. It's talking about one dimensional. Of course, if we're in three dimensions, then we have the three-dimensional version of it, but one dimensional is fine for our needs right now. We always have the exact same equation. So you say, well, wait, if we always have the same equation, then what's the difference between one system and another? And that difference is with the potential. Each system is defined by the potential felt by the particle. So if you have a particle just going through free space, then there's no potential acting on the particle. So our V would be 0. For instance, say free space or free particle implies our potential is 0. But we can have other things. We could have an electric field. So maybe we have an electron placed in an electric field. Well, this would mean our potential is some, let's say, rho epsilon x style of potential, where the potential depends on the position. And of course, we could have different systems, and each system will have its own potential. So that will be the difference between the different systems we're going to work on. Each system has a different potential. When you plug that potential into the equation becomes different. So this time what we're going to do is the free particle. And so we say for the free particle, let's draw it out. This is potential, this is space. For a free particle, the potential is just 0 everywhere. And so to write this down, we say potential as a function of position is equal to 0 for negative infinity less than or equal to x less than or equal to infinity. So all this means is when x is equal to anything, v, the potential, is equal to 0. What we're going to find is for different systems, this v will be defined differently. So maybe v will be infinity between x is equal to 0 and x is equal to negative a over 2 or something. We'll have different definitions. But for this one, this is our definition of the potential. This definition we call free space or free particle. So now that we know that, we have our Schrodinger's equation becomes v is equal to 0 everywhere, so we get minus h bar squared over 2m, second derivative with respect to x squared of psi, plus 0, because v is equal to 0, is equal to e times psi. So now this is what Schrodinger's equation becomes for a particle in free space, that is, the potential is 0. Now, what we want to do is solve this equation. This is differential equation. First step I'm going to do is I'm going to bring the minus h bar squared over 2m to the other side. So I get second derivative with respect to x squared psi is equal to minus 2 times m times e over h bar squared times psi. So you see all this stuff, I just brought it to this side, divided it over, in other words. And now I have this equation. The next thing I'll do, and now I know to do these things because this has been done before, I've done it before. Doing these kinds of tricks makes solving the equation easier to follow. And so if you don't realize why I do what I do, don't worry about it. Just understand that if you do these steps, these are just making the ability to solve the equation more easy to follow. So what I'm going to do is I'm going to take all of this stuff right here, and I'm going to call that k squared. Okay, so 2, that's just a number. M, that's the mass of the particle, that's a number. E, that's the energy. H bar squared, that's a number. So all that stuff is just a number. So what I'm going to do is I'm going to call that number k squared. Okay, not k, but k squared. So if I do this, then what I have is the equation, second derivative of psi with respect to x squared is equal to minus k squared times psi. Okay? So this just made it look cleaner. Instead of having all these numbers all over the place, I plugged them all into one constant variable, or one variable I should say, and I call that variable k squared. And so now I see my final differential equation that I need to solve. Now, likely, you've seen differential equations in math class before. Hopefully, you've learned how to solve this type of equation from the math course. But if not, don't worry about it. We're going to solve it the way a physicist would solve it. Look at what this equation is saying. This equation says, from this side, take two derivatives of the function psi, and you get something when you do that. Okay, the right side of the equation says you have psi times some number minus k squared. Okay? So I want to find what is that function psi such that if I take two derivatives of it, I get minus the same psi back, but with a constant out in front. And so the way I would solve this as a physicist, instead of going to the formality of what a mathematician would do, is I would just guess. I'd say, okay, well, what are some functions I could think of that might be right? So, for instance, I could think, well, could it be something like psi is equal to x? Or maybe instead of x, let's say a times x. Well, let's see. If I take one derivative of psi with respect to x, what would I get? I get a, and then I'd take a second derivative of psi with respect to x, and I'd get 0. So does this work? Taking two derivatives of psi with respect to x should give me the same thing back, a times x, but with a negative sign and some other constant on in front. Well, no, this doesn't work. So it can't be that. So it can't be a times x. And of course, it can't be something like kx squared. Let's see what kx squared would do. One derivative of psi would give me 2 times k times x. And then another derivative would give me 2 times k. So did this work? Two derivatives of psi on one side, and I get psi again, which is kx squared. Well, no, I can already see there's no x squared over here. That can't work either. Okay, what next? Another natural thing to try is something like e, exponential. So maybe I could say, okay, what if psi is equal to e to the kx? So if I take one derivative of psi with respect to x, well, I get e to the kx back times k. Okay, now I take another derivative of psi with respect to x, and what do I get? So the k stays. I get e to the kx back again, and then I get another k. So I get k squared times e to the kx. So did this work? Two derivatives gives me psi again. Well, here's psi again. That's good. Times a number. That's good. Times with a minus sign. Oh, I don't have a minus sign. All right, well, what if I suck so this is really, really close. What if I just put a minus sign out inside my e? Well, the first derivative should give me minus k, e to the minus kx. Second derivative gives me another minus k, so that becomes k squared, e to the minus kx. So again, I get psi, I get k squared, but I don't have the negative. So no, that doesn't work either. All right, well, what about sines and cosines? Let's try sine. Psi is equal to sine kx. Okay, let's take one derivative of psi with respect to x, and what happens? Well, first I get a k out in front, and then I take the derivative of sine kx, or sine. Derivative of sine is cosine, so I get cosine kx. Now I take a second derivative. And what happens? I get another k, so I have k squared. Now I take the derivative of cosine. Derivative of cosine is minus sine, so minus sine kx. All right, did this work? Well, let's see. Two derivatives gives me the psi again. Psi was sine kx, so here's sine kx. A negative sign, here's a negative sign, and a number. k squared. Here's a number k squared. Aha, this worked. So this must be an answer. The solution to this differential equation must be sine kx. Now, I'll tell you, and you'd have to verify this yourself, psi is equal to cosine kx also works. Okay? So because both of them work, this must tell me then that the solution to second derivative of psi with respect to x squared is equal to minus k squared psi is that psi is what's called a linear combination of the two answers. So there's some amount of the answer, which is sine kx, and some other amount of the answer, which is cosine kx. Because both sine kx and cosine kx work, then adding them together also works, and it's a more general solution. So now I have my answer. I now know the solution to my differential equation, which means I now know the wave function of a free particle. It is a combination of sine kx and cosine kx, where k is the square root of 2me over h bar squared. And now you see why I made that substitution before of k squared is that stuff, because if I made it k is that stuff, then I'd have sine of square root of k times x, and that just looks bad. So by making a substitution k squared here, that means when I stick it into the sine and cosine, it becomes k. All right, so this is very good. We've now officially solved our first quantum mechanics problem. This wave function gives me all the information I need, or I can possibly have, I should say, about this particle. What kind of energies does it have? Well, look, this K tells me about the energy. There's E there, so if I solve this for E, I know the energy levels of the particle. I could do other more fancy stuff, which we'll learn a little bit later, which is to ask some of the other observables. What's the most likely position for the particle? Or what's the most likely momentum, or things like this. But what's important here is to see the method for setting up Schrodinger's equation for a particular system, solving Schrodinger's equation for that system, that is, you plug in the correct potential, get down to your final differential equation, and then, through whatever means you know how, solve the differential equation for psi. Once you have this psi, you now have all the information in the world you could possibly have. Now, for more complicated systems, the free particle is the easiest system because V is just 0. More complicated systems we're about to have, we're going to have to do a little bit more in what's called boundary conditions to kind of calculate things like, what does this A mean and what does this B mean? But we'll learn how to do that. It's not so hard. All it is 1 or 2 extra steps from what we've already done. What we've done is the critical piece. And it's amazing how easy this actually is. Here's our equation. Knowing what potential we use for our system, plug that potential in for V. We now have the equation for our system. Do our steps. Get down to a final equation. Solve that differential equation. That's the hardest part of everything. Here it was easy. More complicated differential equations, you have to do more complicated versions of solving it. And that's the step which makes it so there's only very few problems we can actually do. If that weren't the case, then every problem in the world can be solved. The problem is this step right here of having our differential equations. We're going to have systems where a differential equation is just not solvable. We don't know how to do it, Or, even worse, it's literally not possible whether we knew how or not. But what we're going to work on are those problems where we can solve them. So anyway, I hope this was enlightening. I hope you got a little bit out of this. Definitely what you're going to find is for the rest of the semester, we are doing this. We're going to have a particular system. We're going to write down its differential equation. If possible, we're going to solve the differential equation. And then using that wave function, we're going to answer questions. So, what I would say is, if this is not clicking very well, go online, go on YouTube, search out Schrodinger's equation for FreeParticle, and watch someone else do it. See how they talk about it. Some are going to be very, very complex. Maybe they're higher level, graduate level classes. Some are going to be at a low level. Listen to what other people say, see how they do things, and it might help unlock a bit of the logic. I'll do my best to do things at a low enough level for us where I don't demand that you remember everything about differential equations. I'm hoping that instead you're going to learn how to do the differential equations in this class. But definitely pay attention to this stuff. This is the heart of quantum mechanics that we're going to worry about. This is the meat of the subject. And so this is where we're going to be for the rest of the semester. So until next time.